Hello all, today our topic is smoothing spatial filter. First, what is meant by spatial filtering? Spatial filtering is a process by which we can alter properties of an optical image by selectively removing certain spatial frequencies that make up an object. For example, filtering video data received from satellite and space probes or removal of raster from a television picture or scan image. Next one is what is meant by smoothing filter. Smoothing is used to reduce noise or to produce a less pixel rated image. Most smoothing methods are based on low pass filter, but you can also smooth an image using an average or median value of a group of pixel or a kernel that moves through the image. Smoothing filters are used for blurring and for noise reduction. Blurring is used in a pre-processing task such as removal of small details, and noise reduction is accomplished by blurring. Replacing the value of every pixels in an image by the average of the gray levels in the neighborhood will reduce the sharp transitions on gray levels. Thus, smoothing can reduce noises desirable and blur edges undesirable. Image smoothing filters, which include the Gaussian, maximum, mean, median, minimum, non-local means, percentile and rank filters, can be applied to reduce the amount of noise in an image, such as removal of small details from an image prior to large object extraction and bridging of small gaps in lines or curves. Noise reduction can be accomplished by blurring with a linear filter and also by non-linear filter. Then next our topic is smoothing linear filters. Linear smoothing filters are good filters for removing Gaussian noise and in most cases the other types of noise as well. A linear filter is implemented using the weighted sum of the pixels in successive windows. The output or the response of the smoothing linear filter is simply the average of the pixel contents in the neighborhood of the filter mask. These filters sometimes are called as averaging filter. Pixel averaging in a spatial domain, that is each pixel in the output is a weighted average of the neighbors, and second one is a convolution whose weight matrix is sum to the 1. We already discussed that this filter is sometimes are called as a averaging filter. Then next figure shows the 3x2 smoothing filter mask or the 3x3 smoothing filters. Mark coefficient is given by the following equation, that is R is equal to W1 Z1 plus W2 Z2 plus dash 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 up to plus Wmn Zmn, that is summation of k is equal to 1 up to m into n, that is Wk Zk is equal to Wt W raised to T Z. This is the mass coefficient equation. The idea behind smoothing filter is straightforward. By replacing the value of every pixel in an image by the average of the intensity levels in the neighborhood defined by the filter mask. This process results in an image with reduced sharp transition in intensities because random noise typically consists of sharp transition in intensity levels. The most obvious application of the smoothing is noise reduction. However, the edges, which almost always are desirable features of an image, are also characterized by sharp intensity transitions. So, averaging filter have the undesirable side effect that they blur edges, and other application of this type of the process include the smoothing of false contour that result from using an insufficient number of intensity levels. A major use of averaging filter is in the reduction of irrelevant details in an image. By irrelevant, we mean the pixel regions that are small with respect to the size of the filter mask. This latter application is illustrated in a later section. That is, the figure here shows the 3x2 smoothing filters, which is the average of the intensity levels of the pixel in the 3x3 neighborhood defined by the mask. We are as we discussed earlier. Note that instead of being 1 upon 9 coefficient of the filter are all 1s. The idea here is that it is computationally more efficient to have coefficient value 1. At the end of filtering process, the entire image is divided by 9 and m by n mask would have a normalizing constant equal to 1 upon m into n. A spatial averaging filter in which all the coefficients are equal sometimes is called a box filter. As we substituting the coefficient of the mask into above equation, we use r is equal to 1 upon 9 summation of I is equal to 1 up to m up to 9 zi. The second mask in figure shows is a little more interesting. This mask is a so-called weighted average, terminology used to indicate that pixels are multiplied by different coefficients, thus giving more importance weight to the some pixel at the expense of other. In the mask shown in figure B, the pixel at the center of the mask is multiplied by a higher value than any other, thus giving this pixel more importance in the calculation of the average. The other pixels are inversely weighted as a function of their distance from the center of the mask. The diagonal terms are further away from the center than the orthogonal neighbors by a factor of root 2, thus are weighted less than the immediate neighbors of the center pixel. The basic strategy behind weighing the center point the highest and then reducing the value of the coefficient as a function of increasing distance from the origin is simply an attempt to reduce the blurring in the smoothing process. We could have chosen other ways to accomplish the same general objectives. However, the sum of all the coefficients in the mask in figure B is equal to the 16, an attractive feature for a computer implementation because it is an integer power of 2. In practice, it is difficult in general to see the difference between images smoothed by using either of the masks in figure or similar arrangements because the area spanned by these masks at any one location in an image is so small. With the reference of the above equation, the general implementation for filtering an m by n image with a weighted averaging filter of the size m by n, that is m and n are all, is given by the following expression, that is g of x comma y summation of s is equal to minus a to a summation of t is equal to minus b to b w of st f of x plus s comma y plus t upon summation of s is equal to minus a to a summation of t is equal to minus b to b w of s comma t. The parameter in these equations are defined as before. It is understood that a complete filter image is obtained by applying for x is equal to 0, 1, 2, dash dash up to m minus 1 and y is equal to 0, 1, 2, dash dash up to n minus 1. The denominator in equation is simply the sum of the mass coefficients and therefore it is a constant that need to be computed only once. This figure shows image smoothing with masks of various sizes. The effect of smoothing as a function of filter size illustrated in figure, which shows an original image and the corresponding smooth results obtained using square averaging filters of sizes m is equal to 3, 5, 9, 15 and 35 pixels respectively. The principal features of these results are as follows. For m is equal to 3, we note a general slight blurring throughout the entire image, but as expected, details that are of approximately the same size as the filter mask are affected considerably more. For example, the 3 by 3 and 5 by 5 black squares in an image The small letter A and the fine again noise show significant blurring when compared to the rest of the image. Note that the noise is less pronounced and the jack border of the characters were pleasingly smooth. The result for m is equal to 5 is somewhat similar with a slight further increase in a blurring. For m is equal to 9, we see considerably more blurring, and the 20% black circle is not nearly as distinct from the background as in the previous three images, illustrating the blending effect that blurring has on objects whose intensities are close to that of its neighboring pixels. Note the significant further smoothing of the noisy rectangles. The results for m is equal to 15 and 35 are extreme with the respect to the sizes of the objects in the image. This type of aggressive blurring generally is used to eliminate the small objects from an image. For instance, the three small squares, two of the circles, and most of the noisy rectangles areas have been blended into the background of the image in figure F. Note also in the figure the pronouns black border. This is the result of padding the border of the original image with zeros, that is black, and then trimming of the padded area after filtering. Some of the black was blended into all filtered images but became truly optionable for the images smooth with the larger filters. As mentioned earlier, an important application of spatial averaging is to blur an image for the purpose of getting a gross representation of objects of interest, such that the intensity of smaller objects blend with the background and the larger objects becomes blob-like and easy to detect. The size of the mask establishes the relative size of the objects that will be blended with the background. As an illustration, consider the figure A, which is an image from the Hubble telescope in orbit around the Earth, and figure B shows the result of applying a 15 by 15 averaging mask to this image. We see that a number of objects have either blended with the background or their intensity has diminished considerably. It is typical to follow an operation like this with a thresholding to estimate the objects based on their intensity. The result of using the thresholding function of figure B with the threshold value equal to 25% of the highest intensity in the blurred image is shown in figure C. Comparing this result with the original image, we see that it is a reasonable representation of what we would consider to be the largest, brightest objects in that image. This is all about the figure shows. This figure is an image of size 528 by 485 pixel from the Hubble Space Telescope, and B is the image filter with the 15 by 15 averaging mask, and C is the result of thresholding, and image B result of thresholding of image B, that is the original image courtesy of NASA. Then what is meant by nonlinear filters? The general idea is nonlinear image filtering is that instead of using the spatial mask in a convolution process, the mask is used to obtain the neighboring pixel values and then ordering the mechanisms produce the output pixel. Order statistic filter are nonlinear spatial filters whose response is based on ordering, that is ranking the pixels contained in the image area encompassed by the filter and then replacing the value of the center pixel with the value determined by the ranking result. The best known filter in this category is a median filter, which as its name implies replace the value of the pixel by the median of the intensity values in the neighborhood of the pixel. The original value of the pixel is included in the computation of the median. Median filters are quite popular because for certain types of random noise, they provide the excellent noise reduction capabilities with a considerably less blurring than linear smoothing filters of the similar size. The median filters are particularly effective in the presence of impulse noise, also called salt and pepper noise, because of its appearance as a white and black dots superimposed of an image. Opposite the median of a set of values in such that half of the values in the set are less than or equal to sigma, or it is also known as median, and the sigma and epsilon. In order to perform the median filtering at the point in an image, we first sort the values of the pixel in the neighborhood, determine their median, and assign that values to the corresponding pixel in the filter image. For example, in the 3 by 3 neighborhood, the median is the fifth largest value. In 5 by 5 neighborhood, it is an 13th largest value, and so on. When several values in the neighborhood are the same, all equal values are grouped. For example, suppose that a 3 by 3 neighborhood has values 10, 20, 20, 20, 15, 20, 20, 25, 100. These values are sorted as 10, 15, 20, 20, 20, 20, 20, 25, 100. Matlab it take the group of 20 separately, which result in a median of 20. Thus, the principal function of a median filter is to force point with the distinct intensity levels to be more like their neighbors. In fact, the isolated cluster of the pixels that are light or dark with respect to their neighbors and whose area is less than m square by 2, one half of the filter area, are estimated by m median filter. In this case, eliminated means force to the median intensity of the neighbors. Larger clusters are affected considerably less. Although the median filter is by far the most useful orthostatic filters in image processing, it is by no means the only one. The median represents the 50th percentile of the rank set of the numbers, but recall from the basic statistic that ranking lends itself to the many other possibilities. For example, using the 100th percentile result in the so-called max filter, which is useful for finding the brightness point in an image. The response of 3 by 3 max filter is given by R is equal to max in curly bracket z of k correspond to k is equal to 1, 2 up to 9. The 0th percentile filter is the minimum filter, is used for the opposite purpose. Median, max, mean, and several other non-linear filters are considered in more details in our next section. Figure. Then next, the figure A shows an X-ray image of a circuit board heavily corrupted by salt and pepper noise. To illustrate the point about the superiority of median filtering over the average filtering in a situation such as this, we show in a figure B the result of processing the noisy image with a 3 by 3 neighborhood averaging mask, and in figure C the result of using 3 by 3 median filter. The averaging filter blurred the image and its noise reduction performance was poor. The superiority in all the respect of median over average filtering in this case is quite evident. In general, the median filtering is much better suited than averaging for the removal of salt and pepper noise. This is all about the orthostatics, means nonlinear filter. Then our next topic is sharpening spatial filter. Then our next topic is sharpening spatial filter. Sharpening filters are used to enhance the edges of objects and adjust the contrast and shade characteristics. In combination with a threshold, they can be used as edge detectors. Sharpening or high pass filters let high frequencies pass and reduce the lower frequencies, are extremely sensitive to shut noise. The principal objective of sharpening is to highlight the transition in intensity. Uses of image sharpening vary and include the applications ranging from electronic printing and medical imaging to industry, inspection, and autonomous guidance in military systems. In the last section, we saw that image blurring could be accomplished in the spatial domain by pixel averaging in neighborhood. Because averaging is analogous to integration, it is logical to conclude that sharpening can be accomplished by spatial differentiation. This in the fact is the case, and the discussion in this section deals with the various ways of defining and implementing the operators for sharpening. By digital differentiation. Fundamentally, the strength of the response of the derivative operator is proportional to the degree of intensity discontinuity of the image at the point at which the operator is applied. Thus, image differentiation enhances the edges and other discontinuities, that is such as noise, and de-emphasizes area with a slowly varying intensity. Then next topic is our foundation. We are interested in the behavior of these derivatives in areas of contrast, gray level, that is flat segment at the onset and the end of discontinuities, step and ramp discontinuities, and along gray level lamp. These type of discontinuities can be noise, points, lines, and edges. Let us consider in some detail sharpening filters that are based on first and second derivatives respectively. Before proceeding with that section, however, we stop to look at the top of the fundamental properties of these derivatives in the digital context. To simplify the explanation, we focus attention initially on one-dimensional derivative. In particularly, we are interested in the behavior of this derivative in areas of a constant intensity at the onset and end of discontinuities, step and ramp discontinuities, and along intensity ramps. As you will see in a chapter 10, these type of discontinuities can be used to model choice points, line, and edges in an image. Behavior of the derivative during the transition into and out of these image features also is of interest. The derivatives of a digital functions are defined in terms of differences. There are various ways to define these differences. However, we require that any definition we use for a first derivative must be zeros in areas of constant equivalence, constant intensity, must be non-zero at the onset of a gray level step or ramp, and must be non-zero along the ramps. Similarly, any definition of a second derivative is must be zero in a constant areas, must be non-zero at the onset and end of an intensity step or ramp, and must be zero along the ramps of constant slopes, because we are dealing with a digital quantities whose values are finite. The maximum possible intensity change also is finite, and the shortest distance over which that change can occur is between adjacent pixels. The basic definition of the first order derivative of a one-dimensional function f of x is the difference of, that is del of f of upon del of x is equal to f of x plus 1 minus f of x. We used a partial derivative here in order to keep the notation the same as when we consider an image function of two variables, that is f of x comma y, at which the time we will be dealing with the spatial derivatives along the two spatial axes. Use of the particular derivative in the present discussion does not affect in any way the nature and of what we are trying to accomplish. Clearly, del of x is nothing but d of f of by dx, where there is only one variable in the function is the same is true for the second derivative. The basic definition of second order derivative as the difference of, that is del square f upon del x of square is equal to f of x plus 1 plus f of x minus 1 minus 2 of f of x. It is easily verified that these two definitions satisfy the condition stated above. To illustrate this and to examine the similarities and the differences between the first and second order derivative of digital function, consider the image, consider the figure. The figure B, that is the center of the figure, shows a section of a scan line intensity profile. The values inside the small square are the intensity's value in the scan line, which are plotted as a black dots. Above, it is in figure A. The dashed line connecting the dots is included to aid visualization. As the figure shows, the scan line contains an intensity ramp, three sections of the constant intensity and an intensity step. The circles indicate that the onset or of the intensity transition. The first and the second order derivatives computed using the two preceding definitions are included below the scan line in figure B and are plotted in figure C. When computing the first derivative at a location x, we subtract the value of the function at that location from the next point. So this is a look ahead operation. Similarly, to compute the second derivative at x, we use the previous and the next points in the computation. To avoid a situation in which the previous and the next points are outside the range of the scan line, we show the derivative computation in figure from the second through the penultimate points in the sequence. Let us consider the properties of the first and second derivatives as we transfer the profile from left to right. First, we encounter an area of constant intensity, and as figure B and C shows, both the derivatives are 0 there, so condition first is satisfied for both. Next, we encounter an intensity ramp followed by a step, and we note that the first order derivative is non-zero at the onset of the ramp. And the step, similarly, the second derivative is non-zero at the onset and end of both the ramp and step. Therefore, property 2 is satisfied for both the derivatives. Finally, we see that the property 3 is satisfied also for both the derivative because the first derivative is non-zero and the second is 0 along the ramp. Note that the sign of the second derivative changes at the onset and end of the step or ramp. In fact, we will see in a figure C that in a step transition, a line joining these two values crosses the horizontal axis midway between two extremes. This zero crossing property is quite useful for locating the edges. Edges in digital images often are ramp-like transitions in intensity, in which the case the first derivative of the image would result in thick edges because the derivative is non-zero along a ramp. On the other hand, the second derivative would produce a double edge on edge 1 pixel thick, separated by zeros. From this, we conclude that the second derivative enhances the fine details much better than the first derivative, a property that is ideally suited for sharpening images. Also, as you will learn later in this section, the second derivatives are much easier to implement than the first derivative. So we focus our attention initially on second derivative. In short, let us consider the definition of for a first derivative is it must be 0 in a flat segment, must be non-zero at the onset of the gray step or ramp, and must be non-zero along the ramp. Let us in short consider the definition of the second derivative is must be 0 in the flat areas, must be non-zero at the onset and the end of the gray level step or ramp, and must be 0 along the ramp of a constant slope. And the definition of the second order derivative is defined by this equation, that is del square f of del x of square is equal to f of x plus 1 plus f of x minus 1 minus 2 of 2 into f of n. This is all about the definition of second derivative. And the definition of the first derivative is, the basic definition of the first derivative in the one dimensional function f of x is del f upon del of x is equal to f of x plus 1 minus f of x. This is all about the definition of first order derivative and second order derivative. Let us consider the basic summary of smoothing spatial filter. What is meant by smoothing filter? Smoothing is used to reduce the noise or to produce a less pixel-rated images. Smoothing is used for blurring and for noise reduction. Blurring is used in the pre-processing tasks such as removal of the small details from an image prior to the large object extraction and bridging of small gaps in lines or curves. And noise reduction can be accomplished by blurring with a linear filter and also by a non-linear filter. This is all about the smoothing filters. There are two types of smoothing filter, that is a linear filter, that is smoothing linear filters, and smoothing non-linear filter. The smoothing non-linear filter is also called as a order statistics non-linear filter. In short, what is meant by smoothing linear filters? The linear smoothing filters are good filters for removing the Gaussian noise and in most cases the other types of noise as well. A linear filter is implemented using the weighted sum of the pixel in successive window. This is a basic summary of smoothing linear filter. And what is meant by smoothing non-linear filter or order statistic filter? That is, in general idea in non-linear image filtering is that instead of using the spatial marks in a convolution process, the mask is used to obtain the neighboring pixel values, and then ordering mechanism produce the output pixel. The order statistic filter are a non-linear spatial filter whose response is based on ordering, that is ranking the pixel contained in the image area encompassed by a filter, and then replacing the value of center pixel with the value determined by the ranking result. This is the basic about the nonlinear filter. This is all about the smoothing spatial filters and their types. Then the basic summary about the sharpening spatial filter is the sharpening filter are used to enhance the edges of objects and adjust the contrast and the shade characteristics. In combination with a threshold, they can be used as a edge detectors. Sharpening or a high pass filters let high frequencies pass and reduce the lower frequency and are extremely sensitive to shutter noise. The principal objective of sharpening is to highlight the fine details in an image or to enhance detail that has been blurred, either in error or as an natural effect of a particular method of image acquisition. This is all about the basic of the sharpening spatial filter. In this lecture, we are discuss about the smoothing spatial filter and sharpening filter. Thank you.